We started off with this slide 41. And we're going to talk on slide 41, which is on your right, we're going to talk about X a little bit more in detail. So we're going to start off, and for most of our examples, X is going to be having only one subscript, namely T. For most of our examples, we're not going to have the I subscript for X, namely we're not going to have individually varying times of observations. For instance, if you look at math achievement, everybody in grade 7 is in grade 7, everybody in grade 8 is in grade 8. So they're all second occasion, everybody is in the same grade. We're not going to take into account repeats of grades or anything like that. But we're going to talk about these time scores because in the SEM framework, certainly we can work with those time scores to represent the growth model in the sense showed on slide 42. So slide 42 tells you the story of a linear growth model, and you need two latent variables to describe a linear growth model, the intercept and the slope. That is eta 0 and eta 1. And you have it shown here. For instance, you have 4 time points. And in this case, you can think of math achievement in grades 7, 8, 9, 10. And we're going to first ask ourselves, do we have equidistant time scores? And that's true in this case, right? We have the same distance between grade 8 and grade 7 as between 9 and 8. It's one step in between. And therefore, we're going to choose equidistant time scores. 0, 1, 2, 3 is one possibility. 1, 2, 3, 4 would be another possibility, but that, as we're going to learn shortly, is a less useful representation of the equidistance. 0 is good to have a 0 somewhere. 0, 1, 2, 3 is a useful starting point for what we want to learn. You could just as well have 0, 0.1, 0.2, 0.3. They're still equidistant. I'm talking about specifying the x's here. And an example of non-equidistant time scores is, in this case, you measure at grade 7, 8, and then 9 and 10, you don't measure the people. You pick them up in 11 and 12 and post high school. So in this case, you have a distance of 1 between grade 7 and 8. But then it's 1, 2, 3, the distance between the second and third time points. So then you have to add 3 to 1. You get 4 to represent that the distance here is bigger than the distance there, right? So 0, 1, but then 4. And then the next time score would be 5 and 6. And in all of this, I'm talking about x sub t on slide 41. I'm talking about these values, which we said we would use for these coefficients here, eta 1's influence on the y's. So here is a non-equidistant case. If you read in the data, you certainly would have scores that were non-equidistant in this sense. Here, they are fixed parameters in the model. We're going to see exactly how you fix those parameters in the model. And again, you can choose it on a different scale, dividing by 10. You still have the same distances, relative distances between the points. And again, if questions come to your mind, mark them down on the slide and we'll get to them. Now, I said that it's useful to have a 0 somewhere for the time scores x. So let's look at the model, the simple model again, and have, for 4 time points, the time scores 0, 1, 2, 3. Why is this 0 useful? Well, it lends an easy interpretation It comes about, for those of you who like formulas, in the following way. You put in the time scores here for y1, the first time point. X is 0. So you have eta 0 plus eta 1 times 0 plus epsilon. So so y1 is essentially equal to eta 0. Eta 1 falls out, right? Except for the epsilon. So we're going to say then that eta 0 is, and you will see this on the following pages written out in words. So now you can just listen. You don't have to write. Eta 0 is the systematic part of y at time 1. Systematic meaning what's here. This is the systematic part of y, and here is the time and individual specific residual. But this is the systematic part of the growth, and I'm saying with time score 0 for the first time point, this term vanishes, and eta 0 will be the systematic part of y at time 1. So it is the starting point at grade 7, for instance. So the intercept is interpreted as starting point or initial status for the growth modeling. And that comes about then with a 0 here. And you will see that, so that's a 0 here. That x is fixed at 0 here. And sometimes you will see, as somebody pointed out, that that arrow is left out. If it has coefficient 0, it's the same thing as if it wasn't even drawn. Now for eta at time point 2, we just put in 1, 2, 3, 4 for t here. Time point 2, eta 0 plus eta 1 times the second time score, which is 1. So then you see that eta 2, or eta 1 really, adds one eta 1 thing. So at time point 1, y1 was essentially equal to eta 0. Now it's eta 0 plus 1 eta 1. And at the third time point, it's eta 0 plus 2 eta 1. At the fourth, it's plus 3 eta 1. So obviously, eta 1 has to do with the change across time, the growth across time. And it's the same increase from time point to time point, 1, 2, 3 increase of the eta 1 value. So it is linear growth. So therefore, we interpret eta 1 as the growth rate or the slope. So that is how you can think of the interpretations. We'll give you, I'm going to give you many different kinds of interpretations as the day goes along. And some of them will, fall by the wayside for particular persons. But I think by repeating it in different ways, ultimately, and in terms of many applications, I think everybody will understand this. Now, if you didn't like what I just said, then look at page 45. In words, interpretation of the intercept growth factor, initial status or level, a systematic part of the variation in the outcome at the time point where the time score is 0. And you can, as I alluded to when we came to the head circumference of mothers who drank, you can pick the time point at 0. That was called centering. It could be the starting point or the ending point after 36 months. And we'll show you exercises of that. But in any case, that's where the 0 time score, which is for eta 1, lends you a convenient interpretation of eta 0 as a systematic part of the variation in the outcome, or just think about the outcome at that time point, which is the first time point in my previous example. So then what about the, and that has unit factor loadings, like we said, factor loadings 1 for the eta 0 intercept. And what about the slope growth factor? Systematic part of the increase in the outcome variable for a time score increase of 1 unit. So that tells you the growth rate, how quickly people grow. What about the parameters? Well, you have to remember now that eta 0 and eta 1, the intercept and the slope, are variables. So a variable can have many parameters related to it. Certainly has a mean, has a variance, and can be having regression coefficients connected to it. You can regress it onto variables. You can let it predict variables. So we're going to talk about growth model parameters. For the intercept growth factor, we have the mean, interpreted in words like this, average of the outcome over individuals at the time point where the time score is 0. say the first time point, grade 7. It's the intercept of the average growth factor, also called initial status. If it's a first time score, that's 0. And it has a variance, which tells you the heterogeneity of individuals. So how much do kids vary at grade 7 over there on the left? What variation do you have? That's the variance of the intercept now if you chose the x0 to be 0. If you chose a time score to be 0 here for the first time point. Then eta is, the variance of eta is the heterogeneity among people at the starting point. This quickly becomes very easy for you, I promise. So here you have it laid out, linear growth slope factor parameters, mean, average, variance, variance, covariance. Very often those who start higher grow faster, so you have a positive covariance between the intercept and slope. And then some other things. Then now I'm referring back to what we taught in March in the CFA context. When we talk about a measurement model is consisting of intercept plus factor loadings times the factors. Intercept plus factor loadings times the factors plus a residual. It's fun. It gets a little complex here in the sense, in words, because we have not only an invisible 1 here, but it's preceded by an invisible 0 intercept. So you may write this on the right-hand side of the equality. You may write 0 plus 1 times eta 0. For those of you who took factor analysis here, these are two factors. The factor model, however, has an intercept term here. We called it nu, N-U, in the factor analysis course in March. It's not present here. If you come from a SEM CFA world, the intercepts are not estimated. They're fixed at 0. And if you were here in March, we talked about measurement invariance, equality of measurement parameters across time or across groups. And you can think of that fixed 0, which is then a fixed 0 at all of the time points, sitting up here, nu1, nu2, nu3, nu4. Those intercepts are equal in that sense, which then reflects measurement invariance assumptions across time, which we'll talk about tomorrow morning in a sense. If you're going to study change of people across time, the measurement instrument cannot also change across time. So you have an invariance, measurement invariance across time that you want to have as a basis. Residual variances, these are the variances of the epsilons. They carry the time-specific variation and measurement error as well. And certainly the variances for these epsilons could be different across time. They're held equal across time when you take the two-level approach, but you don't need to do that. You have the flexibility of letting them be equal in the, be unequal in the multi-level, sorry, in the multivariate single-level approach. Now let's take a further look at an example here. Let's take a look at slide 48. And these slides then connect with the SEM formulation of growth models. So this should be very easy for those of you in March. This is a growth model without any covariates. You only have the observed variables being the outcome at 4 time points. The growth factors, eta 0 and eta 1, are not regressed on any covariates down here. This is often called the unconditional model, the unconditional model. Conditional model being the one where you have covariates. You condition on the covariates. Now, if you look at this, it could be representing a growth model where these are random effects, or it could represent a two-factor CFA, confirmatory factor analysis model, because the loadings have a specific structure. You go beyond the exploratory model, exploratory factor analysis, to a CFA. So if you look at this model, you have linear, say that we have linear growth over 4 time points, no covariates. We're going to make a distinction between the H1 and the H0 models. H1 model being a totally unrestricted model, and H0 being the model that we're interested in, the growth model that we're interested in. And in this case, a linear growth model, therefore having 2 growth factors. Now, from an SEM CFA perspective, this model is a model for a mean and covariance structure. Means and covariances are modeled by this model, and I will show you how. But in the H1 model, if you talk about the means and the variances, they are totally unrestricted. We have 4 means, 1 for each time point, 10 variances and covariances. You get 10 as 4 time points times 5 divided by 2, 20 divided by 2, 10. So you have 14 parameters in the unrestricted model. The parameters in the H0 growth model are 9. So how did they come about? And this could be good to know. You know, even this sounds a little techy. It could be good to know. So you get the number of parameters that you expect. Get the parameters that you expect. So in the output, you can see which parameters you are working with, either through the output or output with the estimates, or through a technical output called Tech1, which will show you explicitly, very clearly, which parameters you're working with. So what are the 9 parameters? The means of the intercept and slope growth factors. The means of these 2 down here. That was the alpha 0 and alpha 1 in the early parts of the discussion of the slides. Then you have the variance of those 2 and the covariance. So 1, 2, 3, 4, 5. And then the residual variances for the outcomes. That's the variance of the epsilon. 6, 7, 8, 9. That's how you get your 9 parameters. Now, when you come from the SEM CFA world, you can then get a chi-square test of the overall model fit of H0 as compared to the totally unrestricted model H1 by a chi-square test with a certain number of degrees of freedom. And the degrees of freedom are very easy to figure. They're simply the number of parameters in H1, which is 14, minus the number of parameters in H0, which is 9. 14 minus 9 is 5. You want, and it's good to have some degrees of freedom. It really is a good, for once, it's a good statistical word for it. It's degrees of freedom. It gives you freedom to make a more realistic analysis. At the bottom of page 49 are the parameters that are fixed just by definition of the growth model. The more general SEM CFA model has its intercepts, the nus I mentioned, NU parameter 0. Loadings for the intercept growth factor are fixed at 1. That's the definition of the growth model. Loadings for the slope growth factor are fixed at the time scores, say 0, 1, 2, 3. And the residual covariances for the outcomes are fixed at 0. So we're saying that the epsilons are uncorrelated across time. Now, some of these assumptions we can relax because we have 5 degrees of freedom to relax. Some of them you shouldn't relax because then you're no longer doing growth modeling. Then you fall outside of the growth modeling framework. So let's take a look at that. Sources of misfit. That's what you're interested in. Well, the time scores for the slope growth factor, 0, 1, 2, 3 in this case. Look, I have not drawn this path. It's 0, so you immediately now see that I've centered, so to speak, at time 1. A.0 is the initial status, therefore. And so here you can draw coefficients 1, 2, 3 for x1, x2, x3, and x4. Those time scores, 1, 2, 3, may not be the best time scores. And we're going to give an example of that in math achievement development corresponding to accelerated or retarded growth over time. Those time scores may need to be modified. That could be one source of misfit, namely nonlinearity. Another source of misfit is that the residual covariances for the outcomes, namely the epsilon covariances, may not be uncorrelated. You know, if in the factor analysis world, we assume that residuals are uncorrelated, right? Standard assumption. They need not be. And in some applications, you may need to allow for correlated residuals. We're going to show you that. Other source of misfit is the outcome variable intercepts may not be 0, or the loadings for the intercept growth factor may not be 1. But those two are in the not recommended section of what you can modify. Because if you modify those two, you're no longer doing growth modeling. And while that might be a good idea sometimes, let's try to stay in the growth modeling framework. So the model modifications that are recommended are that the time scores could be estimated at certain time points, and or that the residual covariances could be allowed to be non-zero. So this then connects with the question, how many time points should you have? So when you write your grant proposals, you clearly should argue for at least 4 time points. We know 4 time points gives you 5 degrees of freedom. So if you make if your model fit is bad, and we'll show you what that means, you want to modify your model, relax some of the model specifications, either that or both. And you have 5 things that you can relax because you have 5 degrees of freedom. So for instance, if you wanted to have residual correlations here, say between adjacent time points, you would have 1 here. You can draw a double-headed arrow here. So you're saying epsilon 1 and epsilon 2 are correlated. Why would they be correlated? Well, maybe you have left out some time-varying covariates down here that are correlated across time and influence the y's. When you leave them out, they end up in epsilon, in the residual, and make them correlated. So you have 1 correlation here, 2, 3. So that's 3 parameters that you would estimate, and then 3 parameters meaning that you have used up 3 of your 5 degrees of freedom. Then you have 2 more that you can free. So you could free these 2 time scores if you wanted to. So you have time scores 0, 1, free, free. That then relaxes the linearity. And you end up with, you've used up all your degrees of freedom, but you may have a model that's closer to reality, to the real data. So that's the kind of approach that we're going to take. Now, if you only had 3 time points, so this is 3 time points, you want to circle 3 here, and you go through the same algebra, you only have 1 degree of freedom. 1 degree of freedom only. Now, say that you want to correlate these residuals, epsilon 1, epsilon 2, and epsilon 2, epsilon 3. You don't have the 4th time point. Well, that's 2. You only had one parameter that you could let be free. So what do? Well, you could hold those 2 correlations equal, but what if they're not equal? And what if you also need to estimate this time score here? Then you're sunk because you don't have that capability of identifying or estimating those parameters because you have too few time points. So this kind of reasoning tells you that you certainly can do growth modeling with 3 time points and even some limited forms with 2 time points, but you really need to have 4 to be able to have the flexibility that you need to explore misfit. And of course, you may need many more if you have certain nonlinear development that you try to capture. So it's very tied to your type of application ultimately. For those of you who are formula interested, this shows the formulas for how the means and the variances of the outcomes change as a functional model. I was saying that the model implies certain development. Very often the mean increases and variances increase steeply. There are possibilities, however, for having models where the means increase and the variances decrease, having to do with negative covariance between the intercept and the slope. But this is a slide that I won't talk about now. Here's an interesting slide as well. It shows how the model parameters are identified. And I won't go through this slide, but I'll just give you a few hints on how to study this slide if you want to. And it actually is useful for understanding identification and for understanding designs of multiple cohort studies if you are the statistician who has to design a multiple cohort study. So it shows how the covariances between two y's, here it's yt and yt prime. So t is one time point and t prime is another time point. And how that covariance is determined by the model parameters, the variance of the intercept and the slope and the covariance. And it's interesting, that covariance then has 1, 2, 3, 4 terms. And you have then the terms here written out. The variance of eta 0 is captured by this form here. This is, because the variance of eta 0 influences the y's with coefficient 1. So the covariance between this y and that y is simply the same as the variance of eta 0. If you have studied the factor analysis part, you would know that that is exactly, it's the loading times the variance. Here, a variance of eta 1 can be identified as this part, the variance of eta 1 times the time scores here now being different. This is 1, but this is a free time score here, xt prime. Sorry, this time score is also xt, and this is xt prime. And likewise, if you go through this, you can see how you can identify the variance of eta 0, variance of eta 1, and the covariance between eta 0 and eta 1. And just by way of saying that covariances between observed variables is what's used to identify variance parameters. So you better do the right modeling of the covariances. For instance, if you have covariances between the residuals that you haven't modeled, you will misspecify the estimation of the variances. And we'll see a good example of that in the math achievement. So now, just a few pages here that I won't go through totally, but these next 5 pages or so are a reminder of what we went through in March, the background for this, namely topic 1. Estimation, testing, and model modification for growth models that fall into the SEM framework is exactly the same as what we talked about in terms of SEM and CFA. So we're going to talk about maximum likelihood estimation, where we have the basic assumption of normal continuous outcomes y, but where the normality assumption is not a serious one, because we have ML as well with non-normality robust standard errors and chi-square test of model fit. Turns out that the parameter estimates are for ML are very robust to non-normality, but the standard errors and chi-square test of model fit have to be adjusted a bit. But that's implemented and allowed in Mplus using options like MLM and MLR. Sometimes we're going to work with weighted least squares estimators for categorical outcomes, particularly for models that have a lot of random effects. Missing data is handled in this framework, missing data on certain outcomes. Model testing is going to draw on maximum likelihood theory, leading to so-called likelihood ratio chi-square testing. And then you have the non-normality robust chi-square version of that. We're going to look at, who wanted that? An intruder. We're going to look at various kinds of fit indices to help us as an addition to the chi-square overall test of fit. We're going to look at model modifications and the so-called expected drop in chi-square, where lower chi-square is a better fitting model. So this is just a repeat of topic 1 and topic 2. We're going to also talk about factor score estimation, which in this context concerns estimating the individual growth factor values, the individual's eta 0 sub I and eta 1 sub I values. And statisticians call that empirical base estimation. We're going to talk about it as factor score estimation using the so-called classic regression method or base modal method, which is empirical base. And all of that is then in line with SEM. The chi-square, if you focus on slide 56, just the chi-square test, it tests that the model does not fit significantly worse than a model where the variables correlate freely. Correlate freely means H1 is unrestricted. Here it's a free variance covariance model, but it's also, with growth models, it includes a free mean vector. And in this case, we want p-values to be big. In other statistical areas, we want p-values to be small, but here we want p to be big, because p is the probability, in essence, p is the probability that H0 is true. P is the probability that H0 is true, and you've gone to great pains to formulate your H0, so you want the model to be true. So you want p-values to be big, and you don't want them to be less than 0.05. You do not want to reject here. In other branches of statistics, you do want to reject. Just a quick repeat. And then, coming from SEM, you have a plethora of other fit indices. CFI, often used, needs to be greater than 0.96. Root mean square error approximation, test of close fit, less than or equal to 0.05, and some others. So, and you have various references for that on this slide as well. Degrees of freedom for chi-square is very easy. We talked about 5 degrees of freedom for a 4-time point model and 1 degree of freedom for a 3-time point model. Here we say that the p-value of chi-square test gives the probability of obtaining a chi-square value that's less larger or larger if the H0 model is correct. We want high p-values. Degrees of freedom is very easy, much easier than ANOVA. Number of parameters in H1 minus number of parameters in H0. That's how we got 5 for our growth model. And here's a slide that's important. When a model HA imposes restrictions on parameters of a model HB, HA is said to be nested within HB. And we're going to try to look for nested models as a way to find a well-fitting model. So to test if the nested model so one example of that is HA is your H0 model, and HB is your H1 model. In that case, HB, being H1, is totally unrestricted, but it doesn't have to be the case that HB is totally unrestricted. HB has to be just a little bit more flexible than HA. And then we're always interested in testing if the nested model HA fits significantly worse than HB. You know, we want a simple model, parsimonious model HA. Chi-square test is then obtained, and here's a general truth. Difference in the chi-square values for the two models. Using a degrees of freedom, the difference in the number of parameters for the two models. Or equivalently, we're going to see that quite often we don't have chi-square test or model fit for the more general models that we're going to look at here. But what we always have in maximum likelihood is the log likelihood. And the chi-square can be obtained for testing HA against HB. 2 times the difference in the log likelihood values for the two models is a chi-square variate. So for every model you get in maximum likelihood estimation, you get a log likelihood. And if you want to test the nested model, you just you look at the output, you see the log likelihood, and you go in and just take 2 times the difference, and you have a chi-square. And the degrees of freedom is a difference in the number of parameters for the two models, just like we did for the growth model. So, and model modification is the expected drop in chi-square if the parameter is estimated. So you get a model, but you get modification indices for the fixed parameters, such as we will see, the residual covariances. What would happen if you free them? You don't have to run it to say. You can see what the expected drop, that is, expected drop means expected improvement. You want low chi-squares if the parameter is estimated. So this is standard in the SEM world. Statisticians call these modification indices Lagrangian multipliers, but we just call them MIs. Finally, we're going to take a look at two parameterizations as we go forward today. One is the one that we've looked at so far. Namely, we have here written out the invisible zero intercept, in which case you estimate both alpha 0, the mean of the intercept growth factor, and alpha 1, the mean of the slope growth factor. But there's an equivalent parameterization which we're going to use for categorical outcomes and for multiple indicators. Categorical outcomes late this afternoon, multiple indicators early tomorrow morning, where instead of putting the mean for the intercept growth factor here, alpha 0, you fix that to 0 and put the level parameter instead as the new parameter that I keep talking about, the measurement intercept. And have that free still just like that. So it's just moving that alpha parameter essentially up to the level 1. Same model, same exact fit, and the parameter estimate for alpha 0 here is the same as the parameter estimates for nu there. But this approach sort of, this is saying that the intercept is equal across time, and it is more reasonable and more intuitive to think that way when you have multiple indicators. And we also argue that it's more intuitive for categorical indicators. But we'll get to that. So with that preamble, let's just talk about Mplus language a little bit here in this connection. So if you want to do this parameterization 1, how do you get, first of all, how do you get the unit loadings for eta 0 here? Well, you can take, we're going to present you with two approaches. One is then coming from the SEM world, CFA world. You say that the I factor, the random intercept factor, which is eta 0, we're going to get used to, you have to get used to a lot of different notation here. Not in this class, but if you go to read different kinds of books. So I'm going to go between two parameterizations, or two nomenclatures, eta 0, eta 1 on the one hand, and I and S on the other hand. But other books like Reidenbusch and Breitgart are going to talk about pi 0 and pi 1, et cetera, et cetera. Alpha sub I, beta sub I. Anyway, now eta 0 is I. We're saying that the random intercept is measured by y1 through y4 at 1. That says that those x's are 1, or those low factor loadings are 1. Those factor loadings are all 1 that we've talked about. And S is measured by the y's, S being eta 1, that's where the x's come in, the factors, the time scores rather. Those factor loadings are fixed at 0 for the first time point, fixed at 1 for the second, 2, and 3. That's the linear growth model that we talked about a few slides away. So just saying that we have equidistant time scores, all fixed. We center at the first time point, setting the first time score to 0, so we would leave out that path in the picture. That's parameterization 1. We'll show you an easier way to show that in a second. Let me just add to it. We also say that the intercepts of y are fixed at 0. That's the invisible 0 up there in equation 32. And that is within a bracket statement. Those intercepts are fixed at 0, and then we mention I and S in the bracket statement, which says that we estimate the mean of I and S. So when you make your notes here, I and S in the bracket here talks about alpha 0 for I and alpha 1 for S. Those are the means that come out here. So that parameterization 1. Parameterization 2, you start off the same way, I by and S by, but then instead you hold the intercepts, the nus, equal across time. There's no subscript t here. So you have them within a bracket, and then a parenthetical statement 1 saying that all of those 4 intercepts are held equal to one single parameter. That's the nu in equation 35. And then you have to fix the mean of the intercept to 0. So that's fixed at 0. You cannot identify both the intercept and the mean. And then you estimate the mean of S. That's what that says. So if you play with the LSA data, you can easily show yourself that you get the same chi-square test to model fit. All parameters are going to be the same. It's just that the alpha parameter is going to move over to be a new parameter, appear different spot in the output. Okay, all of those little trivialities. Now let's have some examples, have some fun for a change. Okay, you've suffered enough here now. 63, 62. So simple examples of growth modeling. And before you get into growth modeling, you should really take a lot of steps. And people neglect to do that sometimes, and they pay for it. You really need to do a lot of preliminary descriptive studies of the data. First of all, just to check that you're reading the data correctly. Don't get into an advanced model and have all kinds of strange things happening where you don't even know if you're reading the right variables and get the right means, approximate means or variances that you expect, the right sample size. Look for the distributions, histograms, and bivariate scatter plots. Look for outliers, etc. All of that data screening should be done. Then you want to determine the shape of the growth curve, starting from theory, preferably, and or checking in the data, individual plots, which you can do in Mplus. Just go through the data and plot the individual development over time, and to see what kind of growth shape it seems to suggest, or what kind of peculiarities you have in the development. You can also look at the mean plot, but it's really the individuals that we're interested in. And let's skip to this bullet, fit model without covariates. So first do the unconditional modeling, I think is easiest, using fixed time scores. And then modify the model as needed, with the 5 degrees of freedom used up, or part of them used up by freeing things that we didn't want to free. And then you may want to add covariates. So let's see if we can do that for the LSA math data. So here's a Mplus input. We can take a look at this for those, just for a short while, for those of you who are new to Mplus. It's a basic run. So down here in the analysis command, this is a command that ends with colon. You have type equals basic, ending with a semicolon. That would be a good first Mplus analysis before you get into growth modeling. It gives you basic statistics, means, variances, covariances. So here is the data set that I sent to those of you who requested it. It's an LSA data set that we used to study high school dropout. There's no format statement here which says that we read the file in free format. And you can read about all the details of what that means in the user's guide. And the user's guide sits on the website. But if you don't have it, you can also purchase it. There's a fat little book. So you have the names of the variables that are in the different columns of the data set. So here, for instance, it's math in grade 8, 9, 10, 11, 12. And you have the explanation here of some variables, mother's education and home resources that we're going to use as time invariant covariates later on. And you have math course taking, highest math course taken during each grade, which we later on are going to use as a time variant covariate. Now you can do the basic analysis on all of the variables here in the names equal list, or you can subset the variables to a set that's mentioned in the use variable list. Here we do all of them, apparently. And then you can ask for a plot where you can plot get plots like on the bottom of slide 65 on your left using this statement here. You can sit and point, click, and go forward through your data set to your heart's delight. And out comes things like this, sample size 31, about 3,000 people. You get the means for the math at the different time points. 50, 53, it looks like we're increasing by 3.5 here. And then from here to here, we increase by another 3.5 approximately, and here too. It looks like, in terms of the means, it looks like we have linear development, right? Although that's not sufficient. And then we have a covariance matrix here. We use these fancy terms for cocktail conversations. But we know then that on the diagonal is the variance, about 100. So standard deviation about 10, which says that, you know, the increase here, 3.5, is 35% of one standard deviation, 0.35 of a standard deviation, right? The variance increases with time, which is the typical case. People get more and more different. So here the variance is a lot higher. And then we're not good at looking at covariances, so we turn it into correlations at the bottom. Fairly high correlations here across time, which you often see in data. So this looks like an easy data set to model. Easy in the sense that it's often easy to do growth modeling when the means and the variance increase. It's harder when the means increase and the variance decrease, for instance. So let's take a look at this model. And we'll have slides 68 and 69 up at the same time. And we notice the details of this drawing. I and S, you may want to scribble eta 0 and eta 1. You notice that S does not influence math 7. And you immediately know then that x sub 1 is fixed at 0. So we don't even have to draw it. And then we're saying we're going to do linear growth without covariates. So the Mplus input then, if we can ignore the preamble here, which we know about already, and focus on the bold-faced. And we're going to give you two ways of specifying this model. I'm not talking about the two parameterization. I'm talking about one parameterization in two ways. As follows. Here, the factor analysis way of doing it, and down here, simplification. Let's start with the factor analysis. Repeating what we talked about when we talked about how to set up the first parameterization. This is parameterization 1. So you have I measured by math 7 through math 10. Those four indicators, those four observed variables are seen as indicators of factor I with factor loadings 1, at 1. The factor S has three indicators, math 8, 9, and 10. So we say that the loading for 7 is 0, loading for 8 is 1, loading for 9 is 2, 10 is 3. This also tells you 0, 1, 2 tells you that we have equidistance. And the fact that they're fixed and therefore coefficients that don't vary across people says that you do not have individually varying times of observation. So this is totally within the SEM world. You fix the intercepts at 0, that's the new fixing, and you estimate the means of both I and S. So 1, 2, 3, 4 lines. And after a while of doing this, you realize you want to have an alternative language that's tailor-made for growth, which is this line at the bottom here. This is all you need to say for Mplus to behind the scenes do this. Those 4 lines is what you get from this. So you just say I and S. All you really need to know is that you have growth modeling, and that's the vertical bar statement tells you the program that you have growth modeling. You have two growth factors, I and S. You can have ISQ for quadratic growth. You can have ISQC for cubic growth, as we did for the twins, the lonely twins. So you can have at most 4 of these here, naming them whatever you want. And then after the bar, you have the time scores, the x sub t's. This is the language for when you don't have individually varying times of observation. We're also going to see the language for when you do have individual times of observation using the so-called at option. But we'll get to that in a second. So that's simple, right? All you need to know is this. So why didn't I start here at 9 o'clock? Well, because I wanted to give you a little preamble. Here are the model results. Well, actually, I should have 69 on. Well, so the model results are given in 1, 2, 3, 4 columns. Now it's changed in 5.1. Standardized results are printed separately. The first column is the estimates. So it gets written out as a factor analysis model. I is measured by math 7, 8, 9, 10 with factor loadings 1. All fixed. Fixed, you can tell that they're fixed because standard errors are 0. And you don't get the estimate to standard error ratio. You get the 999 instead in that column, saying you can't compute that ratio because there is no, because the denominator is 0. So these are fixed values just by the definition of the model. And down here, S by math 7 through 10, that's where it starts getting interesting. Here you can tell the time scores again 0, 1, 2, 3, which is exactly what we wanted, right? And they're fixed as well, no parameters. But then it starts getting interesting. Here comes the parameters for the means, I and S, 50 and 3.9. Now the intercept for I, since we have time score 0 here for time point 1, we can use the phrase, we center at time 1 at grade 7. Then the mean for I is actually the mean for math 7. So this is actually the mean of math 7. Which doesn't tell you much, right? It just tells you the scale of the measurement instrument. And when you take the ratio of the estimate to standard error, well, let's wait with that for a second. What you are interested in is the mean of S. 3.9, it's positive, which is great, so people get better at math. Here's the standard error. And if you take the ratio of estimate to standard error, you get something that's approximately in large samples normally distributed. And that ratio is what you have in the third column. Excuse me. And that is then an approximate z-score, approximately a normal score. So it's significant if it's greater than 1.96 at the 5% level. So if it's greater than 1.96, it's significant at the 5% level. And here it's clearly significant. In smaller samples with lower growth, it might not be. You have the p-values in the right column. Now the intercepts are 0 by definition here, fixed at 0, so they can be totally ignored. We're just showing the complete output for you. Then what comes here? Well, the residual variances, those are the variances of the epsilons sitting up here on slide 68, epsilon 1, epsilon 2, 3, and 4. They're not given names even here, they're so unimportant. But the variances here then are, you see that they're allowed to vary. In this particular example, they don't vary very much across time. So they could probably fit just as well holding them equal, which you could do if you like. And which you would do implicitly if you do growth modeling as a 2-level exercise that I mentioned earlier, which you can do in Mplus as well. Now, what's more important is variances of I and S. Variance of I, 86, what does that tell you? Well, you have to relate it to standard error, and you see that it seems to be very large relative to the standard error. And that's the first thing. So you have a significant amount of variation in I that is in variation in grade 7, systematic variation. This variation at grade 7 is not all of the variation in math 7, right? The math 7 variance is a function of the I variance and the residual. So you can think regression analysis here. Math 7 regressed on I. Math 7 is not influenced by S, but only by I. The explained part of the variance comes from I, 86. But there is an unexplained part as well, namely 17, right? Sitting up there. If you take 86 divided by 86 plus 17, you get the R squared down here. You can do that hand calculation and check that haven't made a typo. So 83% of the variance in Math 7 observed variable comes from the variance of I. So it's a good amount of heterogeneity in starting point in grade 7 in U.S. public schools. And there's not that much time-specific variance for these data. So for none of the time point, for all of the time points, I should say, R squared is fairly high. In other applications, R squared may be as low as 50%. You have a lot of time-specific variation. Likewise, S has a significant variation. Namely, the growth rate varies quite a bit across people as well. So the fact that you have variation in these two means that you have some variation that you can try to explain by covariates, time-invariant covariates. And you also have the positive relationship between where you started and how quickly you grow. The higher you start, the faster you grow is what this says. It's a covariance. If you ask for a standardized solution in the output, you get that covariance translated into a correlation. It's significant. That was easy, right? Much easier than the preamble, right? Except now you will benefit from the preamble on the first 1.5, 2 hours. You get, I didn't tell you this, you should not interpret this model. You should forget everything I just said. It's wrong. Or at least we don't know yet that it's right. Because you can come up with any model and look at estimates, but you have no idea if the model has any resemblance to the data. And you cannot interpret output for a model that doesn't fit the data well enough. So how well does the model fit the data? Well, chi-square is 86 with 5 degrees of freedom. P-value is small. And remember, we said that p-values should be large here. We want large p-values. We want small chi-squares. Actually, we want chi-square to be approximately 5. The expected value, the mean of a chi-square is the degrees of freedom, right? So when that is equal to 5, we're doing really well, too well almost. It should be a little bit bigger to not overfit. Now, there are these feel-good fit indices like CFI, which is certainly about 0.96, 0.99, looks like an excellent fitting model, showing that they are a little bit too lenient, probably, or this is an overpowered test. Your task is to figure out, with a sample size of 3,000, do I have too much power? Am I finding trivial differences between my model and a better model? Or am I looking at important misspecifications here? That's where your newfound knowledge of neighboring models come in. Now, you try to ignore that, but now you have to pay attention to it. So we go into modification indices, Lagrangian multipliers, which you get from this analysis that I just did. All of this is from just this first run. It will tell you, if you remember, the expected drop, that's this modification index column, expected drop in chi-square, expected improvement in chi-square when you relax your model a little bit. I remember on the left here, this was the 5 degree of freedom model. I'm going to quiz you. We're going to have a trivia quiz at the end, what degrees of freedom are. So this is a warning. So 5 possibilities for misfit can be corrected. Well, I by math 7 and 8 here tells you about the unit loadings for I. Those you didn't want to touch, right? Those were in the category don't touch, because then you're not doing growth modeling. You may be doing something very interesting, but then you have to motivate this tough road to hoe with the editors. But S-by talks about the time scores. S-by is very important. It can tell you deviations from linearity. Maybe the model shouldn't be a linear one. And all the while, you should look for big values. It's the big values that signal that something is wrong. Now, the biggest values come down here in the so-called with statements. And with has to do with covariances. And which covariances do we have in the model that are restricted? Certainly not those, not that covariance between I and S. It's in there already. But it's the covariances between the residuals up here, where in the baseline model, the first model we try, they're fixed at 0. So the program automatically, if you ask for modification indices, will tell you the MIs for the widths. So the MIs for the width statements. So for instance, we have a big one here, 31, for Math 9 and Math 8, suggesting that there is a residual correlation here, correlation between the residuals at grade 9 and 8. Chi-square would improve by 31 points if we allow that. Similarly, another one is big 10 and 8, and another one is 10 and 9. So that then tells you where to go next and where to start using up your 5 degrees of freedom. So here, there's some more modification indices. Let's ignore them for now. Here's your modified model. We add one. You can do these residual correlations in so many ways. Here's a very simple one. That is, you estimate 3 parameters, 1, 2, 3. So you use up 3 of your 5 degrees of freedom. You still will come out with 2 degrees of freedom. If you don't, you've done it wrong. And the only thing you do is you add to your growth model statement, IS bar, that we talked about, a so-called p-width statement. It's a paired width statement. 7 through 9, p-width 8 through 10 says that 7 will be paired with 8, 8 will be paired with 9, 9 will be paired by 10. So that gives you exactly this. So those 3 correlations are captured by this statement here that's bold-faced. Now, that should give 2 degrees of freedom, and we get 2 degrees of freedom. So we started off with 5 degrees of freedom on slide 73 and a high chi-square value relative to 5. Chi-square has now dropped from 86 to 18. In fact, if you just freed one parameter at a time, you would see exactly the drop that the modification indices talk about. But anyway, 18, for only 3 more parameters, over here on the right, we have 3 more parameters, therefore 3 fewer degrees of freedom. The more parameters, the fewer degrees of freedom. Chi-square has dropped from 86 to 18. That's a healthy drop. That's about 70 for 3 parameters. And that's highly significant, saying that each of these 3 residual correlations are probably going to come out with significant Z scores, the normal test. And here they are. Math 7 with 8, 8 with 9, 9 with 10. Here are the estimates. Here are the Z scores, all significant, greater than 1.96. Why the first one is negative, I don't know. I don't know enough about the topic. But here they are certainly positive. And you may ask also, well, what difference does it make? Is this just data fishing, and are we just having too large of a sample and we find these little significant things but they don't mean much? Well, you can ask yourself. On slide 72, for instance, you have the variances of INS in the previous ill-fitting model. Previous ill-fitting model on slide 72. Here are the variances of INS. Here is the better fitting model on slide 79. Better fitting model on slide 79 has these variances. And then, lo and behold, the variance has gone up from 86 to 92 for I, and gone down for the slope from 4.79 to 3.04. So there is a distinct difference here. And why is that? Well, you know, the residual, when you include the residual covariances, you're affecting how the covariance between the y's at different time points gets estimated, gets represented. That refers back to that page where I showed the different ways that the model expressed the covariance between 2 y's. So a seemingly trivial residual correlation affects key parameters of interest, telling you how heterogeneous people are with respect to I and S. So with the better fitting model, you're more heterogeneous when you start, but less heterogeneous in their growth. So that's a truer assessment of what's happening than what you found in the ill-fitting model. So in this case, it looks like, from this practical point of view, I would call this a sensitivity analysis. The better fitting model is not just better because you have a large sample size and you find trivial differences. These differences may not be trivial. These may be important differences. So it seems like you should use this model. And lo and behold, when you do this, look at the residual variances. Now they are very different across time. This is the better specified model. Now you can certainly not impose equality here because the differences are big relative to the standard errors, and you will get a misfitting model. So I think that's an interesting example by using those 5 degrees of freedom that you buy by forcing your review committee to accept a costly proposal for 4 time points. You have more freedom to get a better model. Certainly if you did 2-level modeling here, the implied forcing of equal residual variances would be a hindrance to drawing the right conclusions. This multivariate single-level approach is more flexible. I should say there are many ways to impose correlations on residuals across time. In the user's guide, for instance, you will find a common statistical approach which to impose a first-order autocorrelation among the residuals, first-order autocorrelated residual structure among these residuals. I'm not going to take time to talk about that now because it is in the user's guide as an example on how to set that up. And I'm not the person who has gone through and compared on several data sets which one tends to fit better or not. I'm sure there's some data, some will fit better than others. This is just a very flexible approach. It allows, you can also have a correlation between here and here, between here and here. But at some point, you're going to run out of your degrees of freedom. In any case, that's an example of our first example of growth modeling, folks. Welcome. You survived. Congratulations to this point. We have various kinds of outputs here to look at. If you ask for residuals in the output, you're going to get the estimated model and the residuals, which is the observed minus estimated, observed being the sample quantities, and estimated being those quantities you deduce from the growth model. So you have the means estimated by, this is the model estimated means, and here are the residuals. And on the means, for the means, the residuals seem to be fairly small, except the standardized z-scores suggest that there are significant differences in the means after all here, math 7, math 8, and math 10, which could be a small indication of a misfit to the linear model. You get the same residuals for variances and covariances here, and just looking at them, they seem to be fairly small. We have a special technical report on the website. The website has a section called Technical Reports, where the different kinds of residuals are discussed in detail. You can read about them. Instead, let's take it on to the next level, slide 83 and 84. So now we're going to add covariates. So now we're getting into the so-called conditional model. And it makes, as you go along, you get prettier and prettier pictures. So we were familiar with this part of the picture where W represented time invariant covariate. Now we're going to introduce a possibility of time varying covariates as well. And in line with the HLM literature, certainly Raudenbush and Breich, we're going to call them A21, 22, 23, 24. But this could perhaps be the math course taking grade 7, 8, 9, 10, whereas this could be a home resources background. So you have two kinds of covariates, and generally speaking, I would say that dealing with time invariant covariates is easier than dealing with time varying covariates. So we're going to start with time invariant covariates and then add the complication of time invariant covariates and continue with the complication of time varying covariates later on. We're going to take a very simple example. Two time invariant covariates. This is just the two covariates. Let's see. I'll do 86 here so we have it in the right order. 86 and 87 is what I'm trying for. So first of all, down to the nitty-gritty details. How do we specify this in Mplus? You have now a measurement model up here, a structural model down here, or in other words, you have a level 1 model and a level 2 model, so to speak, in multi-level terms. But we still take the multivariate single-level approach. The list of variables that we use, the use variable list, we add to the math variables two background variables of the student, namely their mother's education and the home resources. And we still have the growth model here, using the bar statement, the growth model approach of specifying it. And all we add is that we want to regress I and S on these covariates. And then we use the on option, the on keyword, for regressed on. So that says that I, over on the left picture, I is regressed on mother's education and home resources, a linear regression, and S is regressed on mother's education and home resources. So this is parsed as I on the two and S on those two. And now, if you want to go back to the factor analysis language, it's given as below here, but we can ignore that. So that's very easy to do, to say. And you get a model fit here, which seems to be a little bit closer between the chi-square and the degrees of freedom. We're indicating that, when we add these covariates, we're adding a lot more content to the model, because we're saying that those two covariates influence the outcomes only via I and S. No direct influence, only the influence is only indirect, which imposes a structure on the covariances between the x's and the y's, so to speak. And apparently that structure fits very well here, relatively well. So although we know that there is some misfit due to residual correlations here, it's gotten hidden a little bit by the relative well-fitting idea of these covariates having indirect effect. So this number is a little closer to the degrees of freedom than before. These fit indices are happy all the time. They're very good. Anything above 0.95 is what the literature says is good, although that's a very debated topic. Let me just say MLR. What is that? That's a way to, MLR stands for, R stands for robust, ML for maximum likelihood. So this is a way to get non-normality robust results. So somewhere along the line, you want to check, are my data normal? The maximum likelihood estimator builds on that assumption, but it's not a critical assumption. And we often see people wanting a normality test, the old-fashioned normality test of, Mardia's test of multivariate skewness and kurtosis and the like. And I always get the feeling, why do you want to test that? It's, if it is significant, you will find out by instead taking an ML, instead of the ML estimator, you use MLR or MLM, and you check, did that change the chi-square? And I don't think it did very much. 33.6, 33.3. It goes down a little bit. The lesson is that if you have strongly non-normal variables, chi-square gets inflated. Non-normality gives inflated chi-squares. That is, even a well-fitting model could be rejected. Even a well-fitting model could be rejected just because you have non-normality. Chi-square gets inflated by non-normality. Likewise, standard errors get deflated by non-normality that gets ignored. So standard errors are too small if you ignore non-normality. So you get too many significant effects if you ignore non-normality. But both chi-square and standard errors can be computed in a non-normality robust fashion. Here we see it for chi-square. And what I was saying was that chi-square is not that much affected. It's not that much lower, which is then a more down-to-earth indication that you don't have much non-normality to worry about. Often, though, the difference is large, so often you do have that to worry about. But then you just use MLR, chi-square, and MLR standard errors, parameter estimates being the same in both cases, the parameter estimates themselves not being affected by non-normality very much at all. Quite a lot of robustness there. That's the only MLR slide that's inserted there. Estimator equals MLR is how you get it. Here we get back to ML and look at selected estimates on slide 90. And we're focused on the structural part of the model, or what HLM modelers will call level 2. I on the, here the picture is a little skewed here. We have female as well. There should be yet another covariate here. It's a modification I did recently. I forgot to include. So in the picture, you should have female, a box for female down here on slide 86. Female influencing INS as well. So a third covariate. And slope on female mother's education and home resources. So female is a 0-1 dummy variable. Female is 0 for males and 1 for females. Saying that I, how do we interpret I? Well, it is a systematic part of the outcome at the time point where the time score is 0. Time score is 0 for grade 7 because S does not have an arrow from arrow to grade 7. So I is a systematic part at grade 7, namely the initial status of the growth. And at that initial status point, females are higher. So females, other things being the same, have a higher mean on the growth factor in grade 7. So females do better than males in grade 7 is a simple way of putting it, and significantly so. And I is also related to mother's education. The higher the mother's education, the higher the starting point of math achievement in grade 7, significantly so. And home resources as well is significant. So books in the home, computers, or whatever, library, influences the starting point. What about the slope, the growth rate? Females seem to grow a little bit less fast. Lower slope for females is what the negative sign says, but not significantly so. So it should not be interpreted. Not significantly so. Mother's education, the higher it is, the higher the growth rate. Home resources, the more you have, the higher the growth rate, is what this says. So that's the covariate part. You still have S with I and the variances for I and S, but now they are residual variances because they are dependent variables. We don't model the variances, but we model the residual variances. And we don't model the means of I and S, we model the intercepts. Because, you know, if you remember, these are the alpha 0 and alpha 1 intercepts in the regression of I and S on W. So there's a lot, this says that there's a lot of variation left in I, unexplained by the covariates, and a lot of variation left in S, unexplained by the covariates, significantly so. How you interpret an intercept, well, we're not really interested in. That has to do with the scale of the outcome. But how do you interpret an intercept of S? Well, I would say you don't. You don't because, as we will show, the intercept of S does not represent the full mean of S. As we will see shortly now, the mean of S is the intercept plus the slopes times the means of the covariates. And that's where many people go awry. They get upset when the sign of the intercept is wrong without taking into account that the intercept is only a little part of the full mean of S. So we'll show you that here in a second. I'll get back to that topic in a second. Now we have the R square for the outcomes, but now we have not only the math scores as dependent variables, but the I and S as dependent variables. And the R square is far lower for those. 20% of the variance in I is explained, but only 9% of S. It's considerably harder to find good predictors of the growth rate than the starting point. The means, I said that the model, when you have covariates, the model parameters are not the means of the growth factors, but the intercepts. Say that you're interested in the means, well then you ask for Tech 4. Tech 4, which then computes the means for I and S. And I also get the covariates means. How are those means for I and S computed if you really want to know? Well, I'll get to that in a second. Here's the covariance matrix estimated for I and S. You don't estimate the variances for I and S. These things up here are not estimated by the model. You estimate the residual variances, and to which you have to add the explained part of the variation to get the full variance. Here is how all of this comes about. Let's have two versions of this, one for the techies and one for the word-oriented people. Techies look to the left and word-oriented people to the right. And I'm going to watch your eyes now. Put you into two latent classes. Okay, the model on the left, you're familiar with it now. It looks so simple, so much easier than this morning. Y as dependent variable, eta 0, eta 1 as dependent variables. Estimated growth factor means is the intercept alpha 0 estimated plus gamma estimated times the sample mean of W. W with a vertical or horizontal bar really over it is the mean of that variable. So that gives you the total mean of the intercept. It's not only the intercept of the intercept, but it's also the slope of the intercept. Does it get confusing? And then for the slope, the mean of the slope is the intercept of the slope and the slope of the slope times the... You know what I mean. So that's how you get the growth factor means when you have a conditional model. But then you want the outcome means, Y means, and that's the intercept, plus the slope. I'm talking about the E here, E throughout. I should mention that for the non-technical. E stands for expectation. It implies mean in the population, counterpart to the sample mean. So that's sum of the mean of the intercept and the slope times the time scores. And if you go from formula 28 now to the right screen, it's then the output values are plugged into those formulas. Estimated intercept mean, estimated intercept of the intercept growth factors intercept, and then the slopes times the covariate. And you go through, you can follow the output, you have this in the output, and you get the 50.22 which you find in Tech 4. So you could write out of Tech 4 as well here. If you don't want to compute this, get it from Tech 4. Same thing for the estimated slope mean. Any case, remember that intercepts are not the full means, so don't get upset needlessly. Tech 4 is there to the rescue. Some of you probably prefer to just remember these catchy one-liners, right? Oh, not so catchy. Anyway, estimated outcomes for individual I. You also want to have the predicted value, perhaps, for individual I at a certain time point. You know, instead of the wobbly observed curve, you want the smooth function. So that's why, with a little hat over it, for person I at time point t, using A as the intercept estimated and the slope estimated times the time score. And those estimated intercept and slope are estimated factor scores. So you can request factor score estimation, FS, in the output, and get that for each individual. And then you could just, in Excel or whatever you want, compute what the y hat ti is for each individual, which could be used for prediction purposes too. Anyway. Here is 97 just continues getting the mean for the observed variable, which is mean for the intercept growth factor plus mean for the growth factor times the time score, which is 0 at the first time point, 1, 2, and 3 at the other time points. So this is for the observed variable mean, outcome mean. So just showing how it all hangs together. Now, let's look at centering, because we've been talking about it, so it should be easily within reach. Easily within reach for us now. So if you look at slide 99, we've said that the centering determines the interpretation of the intercept growth factor. And the centering point is a time point at which the time score is 0. And we had the example where the first time point had time score 0, x sub 1 equals 0, saying that the slope does not influence the first time point, only the intercept influences the first time point, which gives the meaning to the intercept as the initial status and gives the meaning of the slope to changes, increases or decreases thereafter. A model can be estimated for different centering points depending on which interpretation is of interest. And models with different centering points give the same model fit because they are simple reparameterizations of the model. So if you do the centering differently, you can check that you've done it right by getting the same chi-square. Same model fit. Now, changing the centering point in the linear growth model for 4 time points, that's an example here. Time point 1, 2, 3, 4. We start off with time score 0, 1, 2, 3. But you could change the centering to, say, the last time point, where the 0 would be at time point 4. And there, to still capture equidistance, the time scores would be -1, -2, -3. Just subtracting 3 from the time scores, from all of the time scores. So -3, -2, -1, 0 would reflect centering at the last time point and equidistant linear growth. So it's easy. And applied to this, covariates centered at grade 10. I and S, and then you have the time score at -3, at -2, at -1, at 0. And then I and S on those. And here we've added the P with it as well. So this, I think we had that in the previous model as well. We don't care about the alternative language anymore so much. Now, if you go back then to the previous slides to check that we've done this centering, change in centering correctly, we should get the same chi-square. It looks familiar, 33.6 with 8 degrees of freedom. So the model fit is the same. So why did we do this? Well, we wanted to see if, we changed the definition of I here. Change the definition of I. I is now the systematic part of the growth at grade 10 instead of at grade 7. So we can ask, is mother's education and home resources, do they have the same, are they still significant predictors of where you're at in grade 10 as they were in grade 7? And lo and behold, yes, they are still significant. They didn't need to be. Now the effects are, if you go back and check, they're not the same. These effects are not the same. So you can answer different questions based on these different centerings. So this I can be defined in the beginning or in the middle or at the end, depending on your interest. S will be the same here because you have linear growth, and the growth rate is defined in the same fashion as before. But I changes, which can be used then to your advantage in different applications. Sometimes you want to know where they are at the exit. For instance, if you want to predict something distal, something happening after grade 10, you want to predict from I at the end rather than I at the beginning. So that was easy, right? And now, folks, you have come to the further readings page, which means that we have passed a big hurdle. If you didn't catch all of this stuff that I talked about so far in the first 100 pages, there are 100 to go. You can read about it in any of these sources. Here's a new book, a Wiley book by Ken Boland and Pat Curran. That could be useful. And here's the Duncan and Stryker people from Oregon. And here's a writing that I did with a former student of mine trying to be pedagogical in 1998. Here's an application by Muthen and Muthen for alcohol development. And here's a case where we really utilized the centering, the change in centering point. So we had a quadratic growth curve. And as we will see in a while, the quadratic growth model is a little harder to interpret. The different growth factors, how they relate to covariates, gets a little muddled. And therefore, playing the centering game, namely changing where the intercept is defined, is helpful. So we went through and changed the intercept from ages 18 to 37 to see which predictors were significant at different ages. So that paper might be of interest to you. And I should mention that all of these papers exist in PDF form. If you don't find it on the Mplus webpage, under papers, you can go to the left margins to find papers, growth modeling. Then you find them under my UCLA website. So my UCLA website you find via the Mplus website under About Us, and then click on me, and then you get to my website, UCLA website, where you have a full list of my publications, so you should be able to get that one. Here are the classic Rowden, Bush, and Breich. I find that to be a very useful book, taking the multi-level modeling description of these kinds of analyses, and also then dealing with models that are not growth models but still multi-level, like two-level regression of students within schools, for instance. And Singer and Willett has written a good book on the growth modeling and survival analysis, change being the growth modeling, event occurrence being survival. And for those of you who like a high ratio of words per formula, that's the book for you. It's very nicely written because before they introduce an analysis statistically, they have a chapter that introduces it conceptually. So that might suit some people. And Snyders and Bosker have a good book as well, and I'm sure more are being written as we speak here. So where does that take us? Well, it takes us to nonlinear growth, and we have another 15 minutes here until question and answers. Well, actually, we should take questions and answers now, I guess. Well, let me just whet your appetite here. When we're going to talk about nonlinear growth, we are going to get back into estimated time scores. You know, that other way that you could use up your 5 degrees of freedom. And we're going to talk about quadratic growth modeling and cubic. And we're going to talk about fixed but still nonlinear time scores. We're going to talk about piecewise growth modeling, time-varying covariates in more detail. And what we're not going to talk about is nonlinearity of random effects. That is, models that are nonlinear in random effects, which would take us beyond this course. But this is by way of tempting you to stay tuned after these messages and come back after lunch. But let's take 15 minutes for questions and answers now, because that was a big chunk. Yes? 76?
That grade 10 performance is somehow related to 7, 8, and 9 performance rather than the pairwise correlations that you have there. And because it's sort of a systematic suggestion that grade 10 is somehow, in spite of the intersection and sloping estimated that they are, there's residual going on between 10 and 7, 8, and 9. That suggests that sort of relationship.
Okay, so for those of you who didn't hear that, we're talking about slides 74 and 76. 76 has this p-width inclusion, residual covariances. Slide 74 has the modification indices for the width statements. And we have indication math 9 and 8 for this covariance, and for 10 and 9 over here. 7 and 8 is not mentioned, and then the suggestion is here, looks like 10 is connected with 8, 7, and not only 9, but 8 and 7. So yes, that's looking at further details. So that could suggest that maybe a more involved residual covariance structure could fit even better.
That, I mean, well, so my question is that what it suggests? So that what you're going to be modifying is on the top with respect to the epsilons, or does it suggest something else, like the slope needs to be more skewed towards 10, or is there something, I mean, which side of the model does
the width statements here on slide 74, they talk about how the residuals are connected to each other. And the by statements, however, S, Y, math 7, math 8, they suggest that the 1 and the 2 time scores of 1 and 2 that we use for 7 and 8 are perhaps not perfect. So a slight deviation from linearity is what those two values that I'm pointing to suggest. So this has to do with those two values that I point to have to do with these time scores here. And those values down here have to do with residual covariances up there. Actually, I think this feature that you're looking at here suggests that 10 is correlated with 7, so 10 correlated all the way back to 7. When you have more, I don't know if that's still there, though. Once you've included this, these residual covariances, you want to look at the modification indices again. If you still have math 10 with math 7 significant here, and significant means, it's 1 degree of freedom chi-squared. What's the 5% critical value? 3.84, yes. It's far above 3.84, so it's very significant. Here's the expected parameter change, EPC, by the way. So that's the expected covariance if you free it. Anyway, and here's the correlation in the correlation metric, standardized EPC. Okay. It could suggest that maybe a first-order autocorrelated structure is better, perhaps more parsimonious than doing this, and this. I don't know. We have to look at the modification indices after we've done that. Okay, yes?
Slide 62.
62?
well, what I would expect to be thresholds there, but they're the means for the y.
In here?
62. Over on the other slide.
Yeah.
Yeah.
They're the same here.
Oh, okay. Instead of the thresholds, you're looking at means, and you're setting the intercept mean to be 0. So I'm wondering how you assure measurement invariance across groups or in a latent class scenario if you're not talking about the thresholds of y at all.
Oh, okay. So, yeah. So when we talk about categorical outcomes at the end of today, we're going to make it clear that we don't exactly talk about intercepts anymore. We're going to, the analogous parameter would be a threshold. So then you would say, you would talk about thresholds here being equal. So so you would have $y1 $1 in there instead. So thresholds are held equal instead of the intercept.
But you still set the
Still fix this mean to 0 here.
okay.
Yeah. Right. Yes.
Back to page 74.
7.4.
Within the details of the model, I do understand that we are saying the divided Lagrange indices.
Right.
And my question is the notion of multivariate Lagrange modification is applicable over here? And how it's done?
Okay, so the question is about modification indices or Lagrangian multipliers. And here it is a univariate application in the sense that the modification index that you see here, like 31.3, tells you what would happen, what's expected to happen to chi-square if you free only that parameter. So freeing one at a time. And there's no procedure for predicting what would happen if you free several at a time. So if you want to be very careful, you want to free one at a time and then look at the modification indices again. But I was impatient. Okay, yes?
When you, I guess, slide 74, please.
Slide 74 again.
Yes, thanks. When you were talking about the residual covariances, I know the modification indices suggested putting them, I'm sorry, I mean 76 I meant, I'm sorry, on the picture. When you talked about the residual covariances, we came up with the modification indices, and you mentioned conceptually that there might be some time-varying covariance for which you haven't accounted, so you might want to link them. And I was just wondering from a methodological standpoint, when you have repeated measures, you're assuming probably it's the same person or same measure being used over time. And aside from the degrees of freedom, I mean, would you just want to put those, like correlate the residuals the way they are now, just as a way of forming the model because of the same person or same measure? Or do you think that's captured already in the intercept and slope in the latent indicators?
Yeah, okay, so the question is correlation across time. Do we need these always or not? And that's a good reminder to say that, you know, we talked about 3 approaches to growth modeling, and one of the approaches did not account for the dependency of the data points, namely observations for different time points for a given individual are correlated because it's the same person at the different time points. And I didn't stress that this part of the model already, without these correlations, is a way of modeling the non-independence. The scores for Math 7 and Math 8 are correlated because they're influenced by the same factors, right? So the model here tells you these scores are correlated because they're influenced by the same variables. So the statement would be you model the non-independence across time. It's accounted for in the model. Therefore, it's not a problem. You're not ignoring it. So I would say it's sufficient to do that. This is just extra on top of that. So it's not necessary from that point of view. These residual covariances are not necessary from that point of view. So this, what you're looking at here, the correlation across time, which you can estimate and which you get from Tech 4 at least, correlation between the y's across time is an intra-class correlation, to use the multi-level concept. The correlations between time points for the same people, because time points share the same person. So time points nested within people, but it's modeled here. All right, more questions? Yes, Dr. Dudley.
The simple question on number slide 90.
90.
If I wanted to graph two lines, one for males and one for male and female, and just supposing that the regression of the slope on female is significant, so those estimates are basically the effect of being female, correct? So is that right? So that 2.123 is the effect of the female on the intercept, and the negative 0.134 is the effect of being female on the slope. Yes?
Where did you get the last one?
Slope on female. Negative 0.134.
Right. So this is, you should just think regular dummy variable regression. This is regular dependent continuous variable, and the female is a dummy variable 0, 1 for females, changing the intercept of the dependent variable. So it's saying that I has a higher mean for female.
Sure.
And their females have a lower slope.
Right. So if I wanted to graph those two lines, then would that effect be on the estimated mean for the
Yeah. Estimated mean for I and S.
back in that other that we got later on in one of the other concepts?
Right. Yeah. Yeah. So you could graph it that way.
And then one to follow that up, the mother's education and home resources, they're continuous in nature, and it would make no sense to try to, you just talk about those in the table as opposed to
Right.
dichotomizing those.
Right. And I'm glad you brought that up, because one thing you could do that could simplify the interpretation, you know, we talked about the intercepts of intercepts and intercepts of slopes and all of that jazz, and had to go to Tech 4. If you center your covariates, and now I'm talking about centering in another meaning, that is, if you subtract the mean, sample mean from these two continuous variables, it's perhaps easier to interpret the results, because when you get rid of the sample means, and you look at, and you want to know the mean of the growth factors, the mean of the growth factors are identical to the intercepts of the growth factors, because the mean of the rest is 0, right? Cancels out. So if you centered, you do so-called grand mean centering of these two continuous variables, and then the intercept for I would be the mean for I. You don't want to grand mean center this, because you're not interested in an average female-male person. You would get the mean of I for males. And same for the S part here. Okay, more questions? Yes?
I was wondering, slide 56, you talked about robust standard errors, MLR. Just relating to that, to the statement, with the robust standard errors, is there a point where that breaks down? For example, I'm thinking in particular, sometimes I work with very much smaller data sets that are physiological in nature. Many, for example, 40 individuals as opposed to 3,000 per se. Is there a point where you really can't rely on the robust standard errors anymore that separate down at some point with smaller samples, or are they robust regardless of sample size?
Yeah, so that's a good question. So standard errors here, be they non-normality robust or regular standard errors, the quality of them depends on the sample size. So there comes a point where standard errors are printed are estimated standard errors. So you have an issue of what's the quality of the estimation, and that quality deteriorates at some point when the sample size goes down. Now, what saves you with longitudinal data is that you have repeated measures across time. So if you have 40 subjects, you don't really have the real sample is not really only 40. You have 10 time points. It's not like you have 400 subjects, but it's somewhere in between 40 and 400. Where you are depends on the size of the intraclass correlation. The lower the intraclass correlation, the closer you are to having 400 people. When the intraclass correlation gets close to 1, you have just 40 people. So the longitudinal setting benefits from, it's beneficial for the quality of the standard errors. But you can't really, and I would say that's true for both the normal theory-based standard errors and the non-normality robust standard errors. It's hard to say how far down you can go, and that's really why we've included the Monte Carlo simulation section. You really have to Monte Carlo it out to know for your specific setting number of time points, size of interclass correlation, and the like. But I think you're in pretty good shape, but I can't say exactly what combination of time points and sample size. If you want to read more about that, there is a paper that we referred to at the end of today, a Muthen and Muthen 2002 paper in the SEM journal on Monte Carlo simulation. Okay, more questions? Yes.
A related question, I think. It sounds like when you're talking about MLR and ML, that you're saying you're advising merely running ML and MLR and comparing to chi-square, and if they're quite different, use MLR and forget about adjustments or transformations, just basically say, in other words, using MLR is sufficient protection against violations of normality.
Yeah, from a practical point of view, I use ML and then I use MLR and I check not only chi-square but the standard errors. And if they don't vary very much, I don't worry about it.
But if they do vary, then you just use MLR and call it a day, or you go back?
I use MLR, but I don't quite call it a day. I worry about the non-normality robust results when you have extreme situations, like the ones we're going to talk about first thing tomorrow morning, floor effects, ceiling effects. When you have a high percentage of piling up at the end of scales, these non-normality robust techniques are not enough. When you really need them, they're not there. So, because then not only do the standard errors and chi-square get affected, but even the point estimates get affected, which implies you have to change the model. And that's what we're going to do tomorrow morning, changing the model. But other than that, I don't worry too much. Yes?
At what point do you have to worry about overfitting your model from using the modification indices?
Yeah, that's a good point. Modification indices can certainly lead to fishing around in your data and finding features in your data, including parameters that then will not show up in another independent sample from the same population. So I wouldn't go very far with these modification indices.
Why didn't you start with 8 and 10, math 8 and math 10, because that had the largest drop in chi-square?
Well, I didn't do it that way. I saw that large modification indices existed among the residual covariances. And then I said, well, then let me include all of them, because it makes sense that the residuals could be related across time because of left out time-varying covariance, like map course taken, and many, many other factors. So I sort of made a substantive judgment on top of a statistical index to include that.
So you're...
But it's a tough thing to know when you've gone too far. I certainly wouldn't pick out every single modification index that's bigger than 3.84. In fact, our default is 10, which is conservative in a way. You really want to look for the big signals in the data. But more specific than that, it's hard to do.
With the autoregressive So we have an all-regressive 1 option or 2, whatever it is.
Right.
That would, in this model, would still reduce our degrees of freedom by the same amount, because you're just allowing the diagonals the diagonal of that matrix to,
I think the autoregressive correlation is just one parameter. Yeah, instead of 3 in this example.
because it fixes them to be opposites of one another.
Yeah, exactly, the product. So it'll be R squared, R3, R to the power 4, etc. More questions? I saw several hands. Yes.
Can we go back? I'm sorry. I had it nervous. Slide 49. You went through and kind of described what each one of the degrees of freedom was. I was just wondering if you could repeat that again as you're going through.
Yeah, no good. So 49, and we had 9 parameters in the H0 model listed here. And the H0 is nested within H1. In this case, we talk about H1 being the totally unrestricted, which is what we usually work with in SEM and CFA. You have 14 parameters here. So you get 5 degrees of freedom, being the difference between 14 and 9.
Can you kind of explain where the 9 comes from?
Oh, where the 9 comes from?
Yeah, I'm sorry.
Okay, there are 2 means. 2 means here. 2 variance is here. 4. 1 covariance, 5. And the residual variance for each of the 4 time points. Yeah, right. But it's good to know, which parameters you should expect to get. Because sometimes, depending on the model complexity and the default setting, you might be fooled. You might have a model that's either fewer or more parameters than you want, than you intended. And that will give to misleading results or too well-fitting or too ill-fitting models relative to what you really wanted. So you should know what to expect. Is that too hard to ask? I mean, I'm seriously asking you. It's hard for software developers to make sure you get what you want. It's easier if you focus on a very simple modeling framework. Like if you only did growth modeling, you could probably simplify it a little bit for you, but you want to do so much more. Anyway, so question here.
Yes, in terms of the modification indices again.
Oh, you liked those, didn't you?
The threshold or the cut point, say what you just said again.
Yeah, so it's a chi-square test, the expected change in chi-square, and it's a 1 degree of freedom chi-square value that's printed, and 1 degree of freedom, significant chi-square at the 5% level is critical value is 3.84. So chi-square modification index that's greater than 3.84, if you free that parameter, you should expect a significant parameter estimate.
So the comment about the default is 10, the default in the program?
Oh, yeah, so the program doesn't print these values unless they're greater than 10 to really force you to only look at the really big ones. But you can ask for 3.84 or even 0. You can put the modification index and then in parentheses 3.84 or even 0 to see everything. Yeah. But it's sort of one way of trying to discourage too much. Just PHIS. Yes?
Just a syntax question, because I'm not an Mplus user yet. On slide 87.
And that's okay. Slide.
Here. Yeah. Slide 87. I have a question, then there's another one after that on slide 100. But just,
Yep, 87.
so slide 87, the analysis statement and then the exclamation estimator equal MLR.
Yep.
Now, what is that syntax for? Is that just to call the MLR versus ML?
Yeah.
Is the exclamation point have a significance to it?
Okay, so good question for the newcomers here. Exclamation point, what's to the right of it is just a comment. So This is, as stated, this is ignored, which means that the default estimator kicks in, which is ML. But when you then delete the exclamation point, MLR kicks in. So it's just a way of pointing to that.
And then the second question is the p-width statement. I notice it's in the top syntax but not the bottom, but these are supposed to be equivalent. Is that correct?
Ah, thank you.
So,
That's a mistake. Yes, the P width should be down there as well.
okay.
All right. Other questions? Don't get lunch yet. There were more people asking. More hands up there. The last thing? Yeah. Okay, so the error is on slide 1. You are benefiting and suffering from a improvement on these two topics I've done in the last couple of weeks and months. So there are some little mistakes that creep in here. One is on slide 100, where the P width statement at the top should be repeated at the bottom for the alternative language to be the same. And I should mention that you know, when these videos then get put on the websites, they will come with the handouts that you have that go with this, with all its warts, or with a few little mistakes that are there. But then there will be a corrected handout also on the Mplus website. So ultimately, there will be a corrected handout sitting there in case you missed something.